Good morning. This is the next video for stats section 5.3. There will be one more video after this one before we finish up the chapter. Okay, so title here says general multiplication rule and tree diagrams. And what you're going to find is the general multiplication rule is only mildly helpful. Tree diagrams are extremely helpful for answering probability questions. So let's start with this. You should recognize this formula as the formula for something given something else. Probably if B given A, it's the overlap over the second one. And remember, I could switch the variables around, but again, probability of something given something else, overlap over the second one. Well, algebraically, if I take that equation and just multiply both sides by P of A, I get this. And this is the general multiplication rule, which is the probability of A intersect B equals the probability of the first one times, not sure why my font is so fat here, but I'm just going to keep going with it, times, that's a times sign, the probability of the second one given the first one happened. In general, the probability of something and something else, you can multiply them together. Like if I'm going to toss a coin twice and I want to know what the probability of getting heads both times, it would be 1/2 times 1/2. Of course, when I toss the coin the second time, the probability, it doesn't matter what happened the first time. But this general rule right here says it's whatever the probability of the first event is, P of A, and then you multiply it by the probability of the second event given that the first event happened. So that's what that rule says. And if I scroll down a little bit here, I forgot on this thing, my marking scroll down. Here it is in that yellow box. Probability of A and B equals P of A times the probability of B given A. So really that's the same formula as the formula for given, just algebraically manipulating it. Just be aware of it. Where this comes into play and is helpful is with tree diagrams. So what I want to do here is show you one example that is in the book and just kind of talk through it. And then there's one check your understanding, I think it is, that we are going to do together. Okay, I will say this, the section of the book there are 3 worked out examples on pages 322, 324, 325. I need you to make sure you look at them all, make sure they all make sense. We're going to look at just one of them together, but it'd be worth your while to look at all of them. Okay, so let's talk about mammograms. So first was one about Roger Federer and serve percentages. Again, I like it a lot, but there's 3 of the same thing. They don't all need to be in the video. That's the first one. Second one talks about visiting YouTube. And again, we've got a tree diagram here. We're going to talk about mammograms. Okay. And I want to show this. All right, I'll kind of go back and forth. Again, I'm going to talk through this one. Then we're going to do an example kind of from start to finish together. All right. So I'm looking at example 18, which is on page, 325 in case you care. All right. It says many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. That would be a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does. That would be a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular region. So we've got 3 bullet points here. And I'm claiming that we're going to turn these 3 bullet points into a tree diagram. First one says 1% of the women age 40 and over have breast cancer. Let's stop with that one. We know that 1% have breast cancer, which clearly means that 99% don't. So I'm going to scroll up and back here to the tree diagram. Look at my tree diagram. Look at in particular the first set of branches. I've got has breast cancer and doesn't have breast cancer. And I've got, there's 0.01 for 1% and 0.99 for 99%. So just that bullet point becomes that first set of branches. Then the second one says, for women who, I'm looking at the second bullet point, for women who have breast cancer, the probability of a negative mammogram is 0.03. Let's just focus on that bullet point. If they have breast cancer, the probability of negative mammogram is 0.03. So again, now we're looking at this up here. For those that have breast cancer, so just we're looking at these, 3% get a negative test. There's 3%, which means the other, that says 0.97. It's a weird font. The other 97% don't get a negative, or get a positive. And then the third bullet point says for women who don't have breast cancer, the probability of a positive mammogram is 0.06. If they don't have breast cancer, probability of positive 0.06. So don't have breast cancer down at the bottom, and there's 0.06, get a positive test, which means the other 0.94 get a negative test. Notice, again, you got to be real clear on what probabilities are doing what here. Let me erase this. Okay. Notice that these two add up to 1. And then these two also add up to 1. Like for any single set of branches, the probabilities have to add up to 1. And then these two also add up to 1. That I want that to make sense. That has to happen. Now, I would argue this tree diagram, we have 4 paths, might be the right word. We have has breast cancer positive, we have has breast cancer negative, we have doesn't have breast cancer positive, we have doesn't have breast cancer negative. To find any of those probabilities, you are going to multiply the probabilities along the path. So this top one, I'm not going to write this out for all 4. This is the probability of, I'll say H for has it, and P for positive. And we're going to multiply, so that would be 0.01 times 0.97, which turns out to be 0.0097, 0.0097. And I could do that for each of the 4 paths. And I'll do that. I'm not going to write out what, I'm just going to write out the final answer. The second one would be the probability of has breast cancer and negative. That's H and, I guess, N, the way I've decided how I'm just turning on my calculator here. If I can find it. There it is. So that second one would be 0.01 times 0.03. Make sure I get my decimals right. Times 0.03. That would be 0.0003. So that's 0.0003. Notice what those first 2 probabilities must add up to. Those first, if I just add up 0.0097 and 0.0003, I in fact get this 0.01. Like that should make sense. It's just breaking that 0.01 into a couple of pieces. And then I'll switch colors here for the bottom half. So then now the next one I will write. This is the probability of what doesn't have breast cancer, which is D, and P for positive. Again, I'm going to multiply those 2 together, and I'm going to multiply 0.99 times 0.06, and I get 0.0594. 0.0594. And then to find the probability for the last path, I multiply 0.99 times 0.94. And I get this equals, I just multiplied 0.9306. Again, those 2 red probabilities will add up to this 0.99. And if I add up, I'm not trying to make this too confusing, but if I tried to pick yellow, is that yellow? Yes. If I add up all 4 of these probabilities, they will in fact add up to 1. Like, that should make sense. Okay, so understand that it's really helpful for me and for you to display a set of probabilities using a tree diagram. Now, we haven't really answered any questions yet. I think the first question may have said, okay, this doesn't specifically say represent the probabilities in a tree diagram, but I'm telling you that's going to be helpful. So let's look at I think it asks two different things. First, it says I'm looking at the problem here. Randomly selected woman age 40 or over from this region test positive for breast cancer. Find the probability that she actually has breast cancer. So let's be real clear what that is asking. So we know that they test positive. It wants to know what the probability that she has it, given the fact that she tests positive. Make sure that I said that correctly. I'm looking for the probability of has breast cancer, given that she tests positive. That's what that asks. So let's see what it does down here. Okay, there it is. It says we want to find the probability of breast cancer given positive mammogram. Now, we have a formula for that. The probability of A given B is the overlap over the second one. So the overlap would be breast cancer and positive. So what is breast cancer and positive? That's one of my four probabilities up here. Breast cancer and positive is this very first one. That's what does it say? 0.0097. That's the overlap. Now, what about the bottom? The bottom here says the probability of positive. I don't think we have that number yet, but we have to recognize that we can find it. So the probability, I'm going to try and squeeze another. Sorry, I'm trying to get green here. Excuse me. So this is going to be the probability of cancer and positive. That was 0.0097. That's the overlap. Now, how do I find the probability of positive? I would argue that of my four probabilities that add up to one, this one right here is positive. And so is that one right there. Like those two both have something to do with positive. So I'd have to add those together to get the probability of positive. One is has it and positive, plus doesn't have it and positive. Both of those. So if I add up I don't have, normally I would write both those numbers underneath that fraction sign, but my font is so big it won't work. 0.0097, not divided by, plus, what's that, 0.0594. That is 0.0691, 0.0691. And I think if I scroll down here, I'll be able to see those calculations down here. There's the 0.0691. So there it is. And I get 14%. Let's think about this. Think that this is an very interesting conclusion here. We found the probability if somebody tests positive, like if you're a female over 40, you go for a positive mammogram, you go for a mammogram and you test positive, this says there's only a 14% chance you actually have breast cancer. That's just a very interesting result. But again, the goal here, the task here is to see how I can use a tree diagram to answer probability questions. Okay, now I want to do the check understanding with you. And I have a smart notebook open, so it's going to be a little easier to do the writing. I've already got it set up here. So let me scroll down here. Okay, here it is. All right, so we're going to do this together. It says, check your understanding. It says a computer company makes desktop and laptop computers at factories in 3 states, California, Texas, New York. The California factory produces 40% of the company's computers. The Texas factory makes 25%, and the remaining 35% are manufactured in New York. Let me stop right there. All that did was that told me what percentage were made in each state. I'm already going to start my tree diagram. As I've already made my tree diagram here, just covered up some of the numbers. So I would argue that the first, let me get this thing out of here. If I could select this and get it out of the way. So there's my first set of branches. It said 40% are made in California, 25% in Texas, and 35% in New York. So all I did so far was, and now those 3% add up to 1. That's just where they're made. Now within each state, it's going to tell us something else. Let's go back to the problem. We'll come back to this tree diagram. Then it says, okay, of the computers made in California, 75% are laptops, which of course means the other 25% are desktop. That's in California, 75-25. So let's go back here. That's in California, 75-25. So if I go here and I go, I want to move this there just for California, 75-25. Again, those two still add up to 1. And then let's go back and look at the other 2 states. I'll get rid of this whole thing at once. It says of those made in, let me get that, good. Those made in Texas, okay, got to be careful you read this correctly. Of those made in Texas and New York, 70 and 50% are laptops. So in Texas, it's 70-30, and in New York, it's 50-50. So now if I go back here and I, in fact, delete that. So now for each state, California, 75 laptop, 25 desktop. Texas, 70% laptop, 30% desktop. New York, it's 50-50. And again, each individual set of probabilities adds up to 1. And now what I can find, what's underneath this last rectangle, for each of I have what, 1, 2, 3, 4, 5, 6 branches, 6 paths. I can find the probability of this and this by multiplying the probabilities. And again, save us the trouble and the time during this video. I did the math already, I think. It is right there. So I have 6 possibilities. Either a computer is California and laptop, or California and desktop, or Texas and laptop, or Texas and desktop, or New York and laptop, or New York and desktop. So I just multiply probabilities. Those probabilities, those 6 probabilities down on the right, do in fact add up to 1. That should make sense that they add up to 1. So part A in this exercise just said to make a tree diagram, construct a tree diagram. But steps 2 and 3 are questions 2 and 3 ask actual probability questions. Problem 2, find the probability that the computer is a laptop. So it wants the probability of a laptop. Well, you've got to know that now that I have all of these probabilities, let me in fact move this over a little bit so I have more space to type here. How do I find the probability of a laptop? Well, I've got a set of probabilities in this column here that all add up to 1. Which ones are laptops? That's a laptop, that's a laptop, and that's a laptop. I just said a laptop. I meant a laptop, of course. So I can literally at this point add those together. That would be 0.3 plus 0.175 plus 0.175. I add those. I think I get, is that 65%? I think it equals. I think that equals 0.65. Looks like 65. I have a 65% chance of getting a laptop. If I had not made that tree diagram, it's a very difficult question to answer. So the question said, make a tree diagram. Oftentimes in the assignment or on your chapter test or on the AP test, if it just asks for the probability of a laptop, it's going to be helpful to make a tree diagram. All right. And of course, if I needed the probability of a desktop, I could add the other one that didn't ask that. So now let's look at this last one. Let me go back, make sure I wrote the question down correctly. It said, given the laptop is selected, what's the probability that it was made in California? So it wants the probability of California given a laptop. The probability of California given a laptop. Well, we now know that's the overlap over the second one. So that's going to be, the overlap is California and laptop. California and laptop, I see that number right there. So that's 0.3. Over the bottom, the second, which is a laptop, which conveniently we just happened to find in the last question. That's that 0.65. Understand, it could have, had it just asked that, like had it started with California given laptop, we would have had to make the tree diagram. The overlap is the 0.3, and then that 0.65 is in fact these 3 added together. So again, I can't emphasize enough the benefit of making a tree diagram in a situation like this. So if I do 0.3 divided by 0.65, I get 0.46. So I think that's my final answer here. Equals, let me go back to a pen, equals 0.46. Again, let me come back here, and I'll go back here and make sure that I'm not making stuff up. The answer to this should be 0.46. Show the answer. Come on, show the answer. Hello. It's acting up on me. It's not actually showing anything. Oh, there it is, 0.462. Okay, good. So there you have it. So again, the goal here is, again, officially this general multiplication rule, it just means I can multiply probabilities to get the probability of this and this. And then more importantly, how to use tree diagrams in order to help with this. Okay, and then your assignment is on page, let's see, I can type this in here. Your assignment is on page 334, and it is just doing number 71 to 80. So that's it for this. Again, one more video that'll probably be posted on Friday morning. So have a great Thursday. Let me see if I can turn it. All right. See you.